Добрый день. Федор, слышишь?
Здравствуйте, Сергей Анатольевич. Да, слышу.
Так, ну мы ведем по-английски, хотя там, я так понимаю, все наши, поскольку это все-таки идет на YouTube, мало ли кто там слушает.
Хорошо.
Значит, как считается, значит, 15-16 минут и на вопросы, наверное, да, ответы?
Да, я вам вопросы буду пересылать в чат Zoom.
Хорошо, хорошо. Мы будем спрашивать людей соответствующим образом.
Здравствуйте, Сергей Анатольевич. Да, слышу.
Хорошо, я тогда не ухожу уже.
Хорошо.
Федор, у тебя прививка есть какая-нибудь?
Нет, Сергей Анатольевич, я болел в январе.
В январе, да? Просто если ты захочешь, говорят, что на полгода хватает, но полгода уже как бы с января проходит.
Да, я понимаю, что проходит. Вот я сегодня узнал о том, что, возможно, потребуется прививка или справка о болезни. Вот.
Ну, если что, у нас прям в МНОЦе, в МГУ начинают прививать.
Понятно, хорошо.
Федор, а ты в качестве заставки какой-нибудь наши вот эти 4 доклада план выведешь или нет? Или я просто... Они у меня...
Да, я могу вывести, но мне Алексей Маслаков сообщил, что изменения произошли. У меня новые заставки нет. У меня есть старая программа от прошлой недели. Я ее могу вывести в виде таблички.
А новые, ну там люди знают, кто в каком...
Ну да, Алексей сказал, что знают, кто должен подключиться.
Хорошо.
Так, сейчас я выведу.
Хорошо.
Сейчас надо поменять. Сергей Анатольевич, просят не начинать секцию, пока пленарное заседание не закончится, чтобы все могли переключиться сюда.
Хорошо. Ждем.
Да.
No sound. Do we have sound? Yes. Now we have.
Exactly. Алексей,
Yeah.
привет.
Привет. Это, я не понял, кто спросил.
It's me.
О, понял, да. Привет. Задержка. Some delay. Video and sound.
Some delay in plenary session.
Yeah, that was very interesting. Two presentations. Very good. Actually, I didn't understand that Diana is what is
Hello,
position?
hello everybody.
Hello, Dima. Do you know what is the exact position of Diana? If she is first mate or is not captain yet?
Pardon, I did not catch what did you say?
Diana Kinji, what is her position?
If I'm not mistaken, she is the second, how to
Second
say?
mate.
Second, yeah.
Second mate, okay.
Second mate.
Sturman, because he said Sturman, Ice Sturman.
Okay, maybe, yeah.
I don't know. Mhm. Good. Good.
Okay. So, colleagues, do we know about end of this plenary session or no? Our session or no?
I think the plenary session is closed, and
Yes,
we can start
we can
sections.
start.
Okay. Thank you. So, our assistant can show us preliminary program of our session, I think. Fyodor, is it possible? Okay. So, we have 80 minutes for 4 reports. So 20 minutes at all. I expect that every speaker will use 15 or 16 minutes, and we have time for 2 or 3 questions, if possible. So the first one, Natalia Sukhich, wind-driven waves simulation for port engineering in the Russian Arctic using MIC by DHI models. Please, Natalia.
Hello, dear colleagues. Yeah, I'm so sorry. I have problems with my camera, but I hope you could see my presentation now somewhere.
Not now, but soon, I think.
Yeah, I just cannot share my slides because I'm not allowed.
Oh, but somebody should.
If we have.
Yeah, because host just disabled my screen sharing.
Oh, but that's strange because you are in the room.
Yeah, yeah. I guess just technical assistant need to allow sharing the screen for participants.
Please help.
Oops.
Okay. We can see the presentation.
Ah, great. Yeah. Can you open it? Okay. Yeah, and today I just would like to present our results, and I have to say preliminary results of our recent work conducted at the Marine Research Center, Lomonosov Moscow State University. And it is about wind-driven wave simulation for port engineering in the Russian Arctic using MIC by DHI models. And yeah, as I said, here are just preliminary results because this work is just our first step for research in this direction. The next slide, please. Yeah, and today I will follow this structure. At first, I will tell you a bit about introduction and our tasks. And the next step will be a short description about region of interest, particular regions in the Russian Arctic. And next, I will tell you a bit about numerical models and modern numerical models, and especially MIC by DHI, Danish numerical model, which we are using for our numerical experiments. And the next part will be briefly about our results. It's like about wind waves in Faraday Bay, which is in the Laptev Sea, and wind waves felt inside port area and in the natural conditions what we have in the Russian Arctic. And I will tell you briefly how we can simulate Boussinesq equation in shallow water environment of the Russian Arctic. Yeah, and some conclusion at the end. Next, please. Yeah, thank you. Nowadays, the Arctic Ocean is a key region. It's interesting from scientific point of view. It's important for industry. It's important for logistics. And the northern route, of course, is located here. And lots of ports and number of construction works is just increasing in recent years. This is from one side, and from another side, Arctic is, of course, characterized by harsh hydrometeorological and ice conditions. And now we see how modern climate change actively and rapidly acts, especially in the Arctic Ocean and Arctic region. Another biggest problem that, unfortunately, the Russian Arctic is rather poorly covered by observation and in situ observations. So in Marine Research Center, we are usually providing hydrometeorological support during engineering works in the Russian Arctic. And due to absence and sometimes lack of observations here, we are using numerical modeling as a powerful tool for description of atmospherical, oceanic, and ice conditions in the Arctic. And now we are looking for a better and modern approach for our studies, taking into account our modern climate change and new technical approaches. So at one side, we should provide precise estimations of parameters of such processes as wind, field, waves, and currents. And from another side, our instruments should be suitable and useful for our particular engineering tasks. So this was just our first step to find this kind of approach. Next, please. Wind-driven waves is usually highly energetic ocean phenomena, mostly driven by wind, of course. In the Arctic, its action are usually limited to ice-free period, but nevertheless, it significantly affects port facilities and constructions and must be taken into account during engineering works. We started our work from tests, how our numerical models can really describe wind-driven waves in the Russian Arctic in the situation when we have the lack of in-situ observations. The region of studies was randomly chosen, and we took the Faraday Bay, which is in the Laptev Sea. This is a semi-closed natural bay in Taimyr Peninsula. And this is a shallow water region. And it's semi-closed, and we can expect some complex transformation of wind-driven waves here due to depth changes. And numerical experiments that we conducted were performed for natural conditions, and several experiments we added potential port facilities, very schematic ones, but we can see how our model can resolve wind waves on the smaller scales and inside potential port area. Next, please. Thank you. In this work, we used MIKE by DHI numerical model. This is a numerical model provided by Danish Hydraulic Institute. This is hydrodynamic nonlinear model, supports unstructured mesh approach and non-stationary approach. It consists of different modules. For example, it's various hydrodynamic module for current simulation, lithodynamic model for sediment transport. And now we are mainly interested in wave models, of course. And MIKE has two different modules. The first one is 2D spectral wave model, which help us to describe wave climate, spectral characteristics of wind waves field. And it can simulate wind waves and swell propagation, growth, transformation, and breaking of wind-driven waves. And the second model is a 2D Boussinesq wave model. This model is very specific, can describe direct traveling of wind wave from a deep water area to shallow water area. It also can simulate transformation, diffraction, reflection, and might be very useful tool for description wind-driven waves inside the port area. Here we would like to test two of these modules in extreme storm events in a Faraday Bay. Numerical experiment divided basically into three groups. The first one is storms in natural bay with a spectral wave model. The second one, storms with port facilities, potential port facilities, of course, spectral wave model. And the third group is for storms with potential port facilities for Boussinesq wave model. The most dangerous directions for our storms are northeast, northeast, and northwest directions. Next slide, please. Yeah, and our results, what we got from our test. Basically, we conducted 8 experiments with spectral wave model with and without port facilities. And the nearest observational station gave us estimations of a mean wave height. It's about 50 centimeters. And the absolute maximum of 200.5 meters. But the observational point is rather far away. Yeah, it's really far away because Faraday Bay is not covered by direct in situ observations, unfortunately. In our results, what we found that significant wave height is between 60 centimeters and 4.2 meters. And the highest wave detected at the bay entrance, especially we can see that the model basically, we can say that the model overestimates wave parameters, such as wave heights, in comparison to observations. Next slide, please. Yeah, here are 2 videos. Is it possible to launch it? Yeah, I just click. Yeah, here are our results from my numerical model. And here are 2 basic storms. The first one, a storm coming from the north direction, and the second one is a storm coming from the east direction. And we can see how our wind-driven wave field is propagating and how waves are transformed inside the Faraday Bay. And what we found, the most dangerous storm event we simulate was a storm came from northwest direction with 1.7 and 3.5 meters of maximum wave height at the bay entrance. And the absolute maximum for this simulation was 6.8 meters wave height. It's rather overestimated in our point of view. And next slide. Yeah, and one more. Yeah. The second group of experiments is experiments for a wave wind field inside the potential port area. We create just very schematic port area in the Faraday Bay. And what we found that in comparison to experiments with and without port facilities, in experiments with port facilities, wave height is usually 2 times lower inside the port area rather than in natural conditions. We found that maximum wave height inside the port area could be from 1.1 to 5.7 meters. And the mean wave direction is from the north. But we didn't find any significant difference in area close to port, but not inside of port. I mean, the wave height close to a port didn't affect by facilities. And the next slide. Yeah, thank you. And here are also 2 videos. When we can see potential very schematic port facilities, and we can see how our wave field is propagating, yeah, from wind coming from east and wind coming from north. We can basically compare how our wave parameters are changing during the storm event. Yeah, next. I guess it's finished. Yeah, and the final one is my 2D Boussinesq wave model, which allow us to solve enhanced Boussinesq equation and describe traveling of wave train inside the port facilities. This is also video, you can click on it. Yeah, great. And it's rather limited in setup parameters, but what we can see here that we have a really clear picture of interferences, and we can see diffraction and reflection of wind waves inside the port facilities and around it. For our experiments, we have 2 experiments with Boussinesq model, with storm coming from north and storm coming from east. And for our experiments, significant wave height is about 2-3 meters inside the Faraday Bay, which is much more realistic. And inside the port area, significant wave height was about 20-70 centimeters, and waves also propagating mostly from the northern direction. But what we found some problems with simulation of wavelengths when we have something like wavelengths about 100 meters for depths of 10 meters or even shallower, which is really not realistic. And it also there are some problems with setup and parameterization, which we are using inside this model, some artificial layers that we have to use, and sometimes it's not really convenient for us to use it for engineering tasks, especially. And next. Yeah, and some of our conclusions. We have shown that MAIC spectral wave model showed appropriate result with some possibility of improvement. For example, our overestimation of our wave heights probably caused by bottom friction parameter, which we can choose and choose different parameters and improve our results. And we did it for our project, and we found that sometimes for some projects we can have a correlation with in situ observations around 0.98 for correlation coefficient, which is rather great for numerical models, I have to say. But for Mike Businesque wave model. It looks like it's not really a good tool for our engineering task, and it has some problem with artificial layer and parameterization. And unfortunately, the options to fix these problems inside the Mike software is just really limited. That's why it would be really good to have something like opportunity to improve it. Yeah, I think it's all. The next something. Do we have a next slide? Oh, yeah, that's all. Thank you for your attention, and I'm happy to answer a question.
Thank you, Natalia. The first question about wind forcing. What kind of wind forcing do you use? Constant wind or some kind of maximum wind with permanent direction or without?
Yeah, for these particular experiments, we described just only storm events. That's why we took constant forcing for some extreme wind parameters, but observed with parameters from the nearest observational station. So the forcing was constant, yeah, for 20.
And what was the maximum wind speed?
We have 4 different directions, and I guess the maximum was about 18-20 meters per second. I guess something like this.
Okay, thank you. More questions, please.
Yeah, I may ask one question and one comment. So then you mentioned that wave period, mean wave period is 5 seconds. So it actually means that wave number is about 0.1 inverse meters. So then it means that if water depth is greater than 10 meters, you cannot use shallow water approximation, which is valid for Businesque equation. So then I think that you should be careful with Businesque equation when you have short wave. Wind wave could be relatively short.
Yeah, thank you.
Yeah, and second comment that when you consider wave in the bay, could be resonance with natural frequency of the bay. So then you may get biggest wave not at the frequency of storm, but in some other situations when these seiches are excited.
Yeah, thank you so much for your comments. Yeah, of course, the first one we realized that Businesque equation model has some problems with shallow water parameterization, and our point was that it would be good to have something like improvements inside this model, because it looks like really great to catch something like a diffraction, a reflection of wind-driven waves inside port. Sometimes it's very important. Yeah, but unfortunately, it's not possible with this particular tool. And for the second comment, yeah, I guess we just need something like a more spectral analysis of our results and detailed analysis. Yeah, but as I said, this is just preliminary results and first step in this topic. Yeah, but thank you for comments.
May I ask a question?
Yeah.
A short one. Natalia, you have mentioned about lithodynamical model of this program. Is it possible to use this complex for erosion analysis of the shores or protective hydrotechnical structures? Thank you.
Yes, my numerical model really has, I guess, also three different models for lithodynamical processes. For example, for sediments and bottom sediments transports, and for littoral and coastal erosion, especially. Yeah, it's possible to use this model for these tasks, but we should be careful, of course, with our parameterizations. The problem with Mike that it's like a closed code model, and we cannot really fix something inside it, I have to say. And especially for Russian Arctic, there are a lot of processes which is influence on our lithodynamics and sediment transport. And we are not sure how precisely Mike can simulate these processes, but we are also starting to test it for this kind of task. Yeah, basically it's possible, but I guess we need some more studies in this topic.
Yeah, okay, thank you very much.
Thank you, colleagues. We have no time and no questions in YouTube. Thank you. The second report for this session, Pavel Shabanov, ice-free period duration changes in the coastal zone of the Kara Sea and the Laptev Sea using satellite data. Pavel, are you ready?
Добрый день. Hello, colleagues.
Thank you.
I'll share. No, I can't share my screen, but so I have to technical help. Yeah, I tried to share the screen, but it was set off.
Fyodor, please help.
Okay. Nope. 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 Okay. Yeah, nice. Well, hello to everybody. My name is Pavel Shabanov, and I'm a climate scientist from Shirshov Institute of Oceanology, Russian Academy of Sciences. And today I'd like to present my preliminary research devoted to ice-free period duration changes in the coastal zones on the Kara Sea and the Laptev Sea using satellite data. And my presentation will extend the previous speech, because I've started to study this topic after a little conversation with the Arkhangelskaya Oblast administration about the estimation of ice-free period for new port building. It was several years ago, and I'd like to present my results. Next slide, please. Oh, this is, yep, yeah. The main interest of my research, very strong links with the Arctic coastal dynamics, and in this topic there is the main thesis that sea ice limits the interaction between the land and the seawater, and the nearshore ice, sea ice cover, and land ice protects the coast from wave and thermal impacts. And the main consequence that the most coastline erosion occurs during relatively short summer ice-free period. And another researchers of climate scientists found that ice-free period duration increased in the Arctic recent decades, but these researchers were focused on the whole Arctic region, and my research is devoted to coastal zone because it has its own features, and the ice-free period changes in the coastal zone greatly affect the coastal infrastructure, especially for oil and gas industry. It's very important for navigation and future navigation through the northern marine road, and of course for the coastal ecosystems. The next slide, please. Yep. one of the main methodology thing of this research is ice-free period definition, because it's not obvious how to determine it, and the state-of-the-art approach based on the sea ice concentration data and the threshold method usage. The chosen threshold, usually it's 15%, is a threshold which split the open water from the sea ice. But when I've started analyze the nearest to the coastal line satellite data, I found data problems, a lot of outliers, very high intervariability. And the traditional threshold method gave me not bad results, but I try to find another method to determine the ice-free period, and this problem was close to and is close to spillover problem when the satellite radiometers had problems on the border of sea and the land, especially in the springtime. And I tried to manage with it with the data solutions. I suggest the advanced threshold approach. And the main idea of this approach is to normalize the annual time series of sea ice concentrations, and to use the sea ice concentration gradients as start and dates markers. You can see the theme of Arctic sea ice dates and periods. And the ice-free period is the blue one, yeah, on the bottom. And the method description is published in my paper in the paper of 2020. Next slide, please. Yeah, this is, you can see the comparison between three satellite sources. I'll explain it a little bit later. And ABC describes the same point. It's point near Marisala meteorological station, Western Yamal Peninsula, for 2012-2013 time period, from January to the March. And you can see the gray line. This is was original data. And the black line is the smooth data. And for Barents Sea, there was no, after the filtering data, there is no absolute values less than 20%. So in this case, for this data source, the threshold method of 15% is not valid. So I decided to combine all satellite sources into one ensemble time series using just a simple median value from the three data for every day, and construct the ensemble time series, and all further results based on this ensemble time series. Next slide, please. I've used three satellite data sources. One of them is from Japanese Aerospace Agency, another one from National Center of Snow and Ice, and the third one is European OSISAF program. They have different algorithms to identify sea ice concentration values from the passive microwave gadgets, but they have the same spatial resolution of 25 kilometers. They cover the time period from for the whole satellite sea ice era, from 1979 till present. And I transformed all the data to percents and apply the moving 15 days median filter to smooth the time series. Next slide, please. Yeah, the region which I chose to analyze is our two Arctic seas, Kara Sea, the Kara Sea and the Laptev Sea. The Kara Sea was described with 63 points, the Laptev Sea with 50 points. The mean distance between the neighborhood points was 35 kilometers. And for every coastal point, the satellite nearest pixel was chosen. As I said before, the ensemble time series were constructed. Next slide, please. As a result, I calculated the ice-free period long-term means and some simple statistics, and also analyzed the tendencies with linear trends for every 130 points over the Kara Sea and the Laptev Seas coastal zone using satellite data. Using the advanced threshold approach, I defined the start date, the end date of the period, and as a simple difference between these dates, I calculated the ice-free period duration. Yeah, next slide, please. So this is long-term means spatial distribution. Left up figure describes the ice-free period start days. The lower end days, and on the right side of the slide, the ice-free period duration is presented. So you can see that there is an obvious difference between two seas, and especially for duration, yeah, the Laptev Seas is described with violet and black colors, when the western part of Kara Sea is full of yellow and orange, and the difference is very high between these two sides, up to twice. Yeah, and for the start dates, we can see another distribution. We see special features for Western Kara Sea, for Yamal Peninsula, for Yugorsky Peninsula, and we can easily find that for the base there is a similarity for start days long-term means values. It means that the sea ice instead became later in the base in comparison with the open coasts. Yeah, and the maximum, so the latest sea ice melt started, of course, on the north of Timor Peninsula. Yeah, for the end days, long-term means the distribution for the Laptev Sea is very uniform, as you can see with the colors, but it's not. But it has high intervariability in the Kara Sea, and so it's interesting to analyze the trends. Next slide. Next slide. Yeah. Next slide, please. No. No. This is bigger pictures for start days and end days. Yeah, but next slide, please. Yeah, this is some preliminary results for the long-term means. You can see the simple statistics, and it's interesting that the mean sea ice-free period duration in the Kara Sea is near 90 days, and for the Laptev Sea is near 70 days. But the minimum of duration is very close in the both seas. while the maximums differ very strong. Yeah, and of course, in the Kara Sea, we can observe the higher standard deviation values, while in the Laptev Sea is very, very low. Now, next slide, please. Yeah, about the trends, because the trend situation with the trends could be described very easy. They are, for the duration of ice-free period, is all positive, and it's statistically significant for the most points over the coastal zone of 2 seas. Some small region of non-significant changes is on the north of Taimyr Peninsula, on the border between the two seas. And in addition to previous presentation, the Fareev Gulf, yeah, all right. We found that there's no strong tendencies, yeah, they're insignificant in the for the ice-free period. So it means that the situation with the sea ice condition is more stable there. But we it's hard for me to interpret, but it's obvious that there is strong changes in the Yamal Peninsula, western part of Yamal Peninsula, which is very active zone for oil and gas industry, and so the wave and the thermal activity for the coastline will increase according to my forecast. Next slide, please. Here you can see the estimations of linear trends, and in the Kara Sea, average trend is near 13 days per decade for ice-free period duration, and it's both processes extended the start days of ice-free period. They become earlier with the rates -8 days, and the end dates of this period, they shift to the later times with a rate 4.5 days. In the Laptev Sea, the situation has a similar distribution, but the proportion of these two processes is not so different as in the Kara Sea, only 3.5 and -4 and -5. Yeah. Next slide, please.
Yeah. 2 minutes, not more, please. 2 minutes, not more.
Okay, yeah. This is one, let's say. And as you can see, for the ice-free period end days tendencies, there is a similar rates for Taimyr Peninsula and for the eastern part of the Kara Sea. And you know that as it was shown on the long-term means figures, the same rates means not the same absolute values in the ice-free period duration, yeah, because but for the start days, the situation is it's not the same. Yeah, we see the strong negative trends in the Kara Sea and not much lower trends in the Laptev Sea. Next slide. Yeah. So as a result, I calculate the long-term means of ice-free period characteristics during the coastlines of Kara Sea and the Laptev Sea, and for me, the further work will be devoted to comparison it with the changes in the open sea because for me now it's not obvious how it's represented in the modern satellite data. And of course, I'll try to compare it with some observations in the coastline, but it's limited, but it can validate the results, because in my opinion, the satellite missions, especially in the coastal zones, they had many false alarms. The estimations of the trends are too high that we can observe using another kind of observations. Yeah, thank you. That's all.
Thank you, Pavel. We have time for one question. Please, colleagues.
One question may I ask. Pavel, thank you for presentation. A question is as follows. If we have the more long period without ice, does it mean that our shores in the Arctic are more subjected to wave erosion? Have you got some ideas about this?
Yeah, of course. The ice free period duration is one of the climate parameters which is positive, has a positive correlation with the coastal retreat rates. Yeah, but it's a complicated problem because it's strongly linked with the time when it extends. You know that storm activity in the Arctic is more often in autumn and extend in the last weeks of autumn season is more critical than the 2 weeks in the May, from my opinion. And but in a common way, yeah, it will increase the efforts of wave and thermal impacts on the coasts.
Thank you. So let's thank you, Pavel. No questions? No. In chat also no. So the next report, group of Dmitry Onищенко, if I'm not mistaken, Shushpannikov,
Yes.
Chumakov, Fomin, Onищенко, operational and extreme sea ice characteristics for eastern shelf of Sakhalin Island. Please.
Okay, thank you. But I see that my demonstration of screen is stopped. Can you help me?
Fyodor, please help.
The button demonstration of screen does not work. Okay. Okay, good. Thank you. Just a moment. Full screen. Do you see my screen?
Yeah, exactly.
Okay. Okay. Good. Okay. Good afternoon again to all participants. My colleague, due to some technical reasons, is not able to give this lecture, and so I will present this study. So, as I said in my plenary lecture, a huge work has been performed over the Sea of Okhotsk to obtain a lot of information about mid-ocean parameters for the whole sea. And one of the main tasks was to obtain information about ice regime, because it's very important for planning marine operations over the Kirinskaya field and future Kirinskaya South field, which are totally subsea. And just a moment, I'm not able to change slides. Okay, thank you. And I can see all something wrong. Okay, anyway, so we understand that designing offshore fields in cold regions inevitably requires a detailed knowledge of sea ice conditions, including operational and extreme characteristics of sea ice. For most areas in the Arctic, including the Sea of Okhotsk, see full-scale data on the ice regime available from the existing meteorological network or obtained as a part of expedition observations are rare and scattered. In application to the shelf of Sakhalin, from one point of view, due to 5 platforms already installed in the shelf, one could say that we should have a lot of information. This is true only in part because all these platforms are located to the north on the area of, excluding Lunska platform, to the north, and in more shallow waters. And the area of interest for us currently are located in water depths more 100 and more. And so some additional information is is required to very high extension. I said about the whole work and only add that the results of dynamic thermodynamic sea ice modeling have to be used to obtain necessary information about ice regime for the whole Sea of Okhotsk, and the space resolution is about 3 kilometers, and time step is 1 hour. And please, next slide. And this information is available for 30-year period. I have, sorry, some problems. I can't see all my, okay, anyway, just some examples are presented here. We use well-known model of ice evolution, sea ice, with some small adjustments. Some examples are given here together with the information obtained via other hydrodynamical models for atmosphere, for water depths, and for waves, etc. In the picture left, it is shown one example of wind speed with a high resolution. The black dot is a point of interest taken for specific study. And we can see that winds are rather high, up to more than 25 meters per second in some specific synoptical situations. In the picture right, we can see the distribution of ocean currents and sea level performed with another well-known computer program in MOM, produced in Russia. And here one good feature was that this InMOM hydrodynamic model was coupled with the sea ice model, and so the results seems seems better than without these sea ice models. Oh, I can change, just a moment. I'm sorry, some delaying with changing screen. Okay, so we have in hands a huge massive of information, including, as I said, ice cover parameters for every hour in every point of the Sea of Okhotsk for the 30 years. So we can use quite usual statistical approaches to develop some statistical deductions from this information, and we are able to derive a lot of tables similar to this one shown on the slide. For instance, we can see that for instance, the large position, 39%, we can obtain rather consolidated ice with 0.9 to 1, and this frequency is about 40% for months. So in March, almost every time we can obtain very consolidated ice. But we don't see from this table, from this information, the thickness of ice. So this should be taken into account. And so there are a lot of another tables containing data on thickness, on velocities, etc. And only combining this information, we can estimate the real ice situations in this given point. No, again, I can't change. Okay, thank you. Another examples of operational characteristics of sea ice that can be used for planning different marine operations. Here we can frequencies of appearance of ice thickness within a given range for all months, and frequencies for ice drift velocity, again given for different months and for different gradation. I omit this, please go to next slide, because my task is to talk about extreme characteristic of ice cover. I let myself to spend some time to give some clarification, because it seems quite interesting, the idea for this research. Well, so we have 30-year period of observation of ice. For instance, ice thickness quantities. For every year, we can find the maximal value. So for 30 years, we can determine 30 quantities, each of which is the maximal value for the corresponding year. We can arrange them in the increasing order. Then we have so called sample of maximal values. We know that to estimate some extreme values with prescribed return period, for instance, one time per 100 years, we need to perform so-called extreme analysis of these quantities. The idea is as follows. We put all these 30 values on a so-called probabilistic paper relating to one or another extreme distribution. Here we use a Gumbel probability distribution, which have the following shape, where h here is ice thickness, and mu and beta are two shape parameters. We see that the graphical approximation is rather good, so we have good substantiation that we can use this Gumbel probability distribution. Then we can estimate from this picture the possible quantities for mu and beta, and then we can use this determined mu and beta to obtain extreme value for ice thickness related to 100-year return period. So this is the rather simple underlying procedure for this. In our case, when we took our 30 years period for ice level, we obtained estimates for mu 1.96 and for beta 0.36. And after that, it's straightforward to estimate these extreme characteristics related to the parameter alpha. Alpha is the exceedance level. It's a return quantity to period t. For instance, for t 100 years, alpha is 1% quantity. So quite straightforward relation. But the interesting thing is, please, next slide. If I take the fixed quantity mu and beta, and if I take from this random distribution a sample with 30 elements within it, and if I repeat this procedure several times, I will come to different results in connection with the 100 quantity value. For instance, in one sample, only 3 meters, in another 387, and sometimes even 486. What does it mean? Is it wrong or no? No, this is quite usual situations, because we should understand that the initial 30 quantities are in fact random sample itself. So the nature gives us only one random sample. And so the result of our modeling for obtaining extreme values give us only a random quantity again. So the estimation of a random quantity is again a random quantity. And in principle, I should determine the probability characteristics of this random quantity. And this can be done using Monte Carlo simulations. That is, we fix mu and beta and repeat our procedure for obtaining extreme values several hundreds of times. And then we obtain the result that this quantity, resulting quantity, is distributed with normal law, with some specific average value and some specific distribution. Next slide, please. And then, using this information in hand, we can construct a new rule for estimating this extreme quantity for ice thickness with specific exceedance level alpha in such a form where we have additional information obtained from our Monte Carlo simulations. the quantity ZQ is responsible for the level of the confidence level for our study. For the normal law, there is a straightforward connection between confidence level and this quantity Z. For instance, for confidence level 90%, this is 1.28, and for 99%, this quantity is 2.33. Definitely, the larger is the confidence level here, ZQ, the larger will be the estimation for the extreme value corresponding to the same exceedance level. Next slide, please. And using this approach, we have calculated a number of extreme values for level ice thickness, for effective ice thickness, for drift velocity, etc., etc. For instance, for April data, extreme value related to 100 return period, we have obtained ice thickness slightly more than 4 meters, but with the corresponding so-called associated value of ice concentration only at the level 0.4. At the same time, for March, we have 3-meter ice thickness, but with very high ice concentrations. So these are two different design situations, and both should be taken into account when designing possible platforms in the future. Similar situations, for instance, for ice drift velocities. At the confidence level 99%, that is only 1% that we could be wrong, we have obtained that in March extreme value for drift velocity is about 1.5 meter per second, and for big concentration ice 0.9, and about the same, even higher drift velocity for February, 1 meter and 81 centimeter with very close ice. What does it mean? The situation in February is much worse than in March? No. In this table, we don't see information about ice thickness, definitely. So we should use additional information to estimate the severity of ice conditions on one or another months. Next slide, please. So I come to conclusion. An approach for obtaining the statistical estimates of the operational and extreme characteristics of sea ice based on the results of the thermodynamic sea ice modeling is presented, and this approach is quite straightforward and mathematically substantiated. The approach is used for obtaining design values for some chosen point located in the eastern shelf of Sakhalin Island, about 50 kilometers from the Lunsky Bay. And it is shown that the most severe ice conditions with consolidated thick ice in the considered region are observed in March and April. In May, ice is thick as well, as we can see. However, ice is very open. So the main conclusion is that at the moment we have a complete information on the whole Sea of Okhotsk, and we are able to obtain extreme characteristics for every point in the Okhotsk Sea, and so give necessary information for those who will design marine operations or offshore structures in this region. That's finish of my talk. Thank you very much. If you have questions, I'm ready to respond.
Thank you, Dmitry. We have time for one question, please.
Yeah, I can. It seems that your talk in some way linked to the talk of Ken Crossdale about specifying of characteristics dangerous for offshore structures, because that's very interesting that you have bigger ice thickness but low ice concentration, and then you may have high kinetic energy of ice fields. And but what about the diameters of flows?
Of what?
Diameters of ice of flows.
Flows, of ice flows. You see, we use the hydrodynamical ice model. The size of a computational cell is about 6 kilometers. 6 kilometers. So all information is averaged over this area.
I see, but you of course can adjust something from satellite observations.
Maybe it's we have compared for some specific data, calculated data and cosmic and satellite data, but again, it's not very easy to compare directly, because every time we have some differences in instant of doing this picture. So it's not very easy to compare directly.
Yeah.
So, okay, only in some quantitative estimations, but in principle, this can be done maybe in future. A huge information, we need time to analyze it.
Yeah, thank you. Thank you. Very interesting. Very good.
Thank you. Thank you.
Thank you.
Colleagues. And now let's go to last report of this day. Alexey Marchenko, Turnbull, Valik Marchenko.
Okay.
Properties of sea ice, ice drift, and surface currents in Spitsbergen Bank.
So then I need to open. So then I don't know why yesterday I had a good access, but now host disabled participation screen share. Maybe it should open.
Fyodor, please help us.
Yeah, unfortunately, definitely some problems with our attempts to share screen.
Strange. Yesterday it was no problem, and I asked before my presentation, could we do the same as yesterday? And they said that's okay, but now I cannot share my screen. The same as others.
Fyodor, please.
I think in the morning with my plenary talk, all was okay, and now definitely
That's
some
strange.
strange thing. Yeah,
I don't know why it is.
some maybe technical problem.
Host disabled participation screen sharing. Participant screen sharing.
You said it's ready. Please.
Okay.
Okay, we see.
Yeah. So then I have many co-authors in these presentations from Canada and from University of Alaska and from Shershov Institute of Oceanology. So then presentation is focused on Spitsbergen Bank. On the right-hand figure, you see Spitsbergen, and to the south of Spitsbergen, between Spitsbergen and Bear Island, there is Spitsbergen Bank. So, and from this figure, you can see positions of ice age. So it is clear that the mean position of ice age near on the Spitsbergen Bank is located more to the south than in the other regions of the Barents Sea. So Spitsbergen Bank is bounded from the south, west, and east by polar fronts, separating water coming from the Arctic and water coming from Atlantic. In addition to polar front, there is tidal front. Tidal front correspond to much stronger velocities of tidal motion on Spitsbergen Bank than in adjusted regions. So then here you see the bathymetry over the Spitsbergen Bank. So blue line is 50-meter depth and red lines 25-meter depth. So most of Spitsbergen Bank is the depth around 50 meters, but to the north from Bear Island, there is a place where a bathymetry map on the bridge show depth 17 meters. Actually, it is dangerous for navigation because a significant wave height for the region is estimated 15 meters and depth 17 meters. So in some storm, actually, ship could hit the bottom in this place. So tide motion is very interesting in this region because we are near critical latitude. Critical latitude for M2 tide is determined by conditions that tidal frequency equal to Coriolis frequency. And that is exactly around Bear Island. So then you see it on the left-hand side, phases of semidiurnal tide calculated by Gievik and Kozars in 1994. There is amphidromic point also close to the Spitsbergen Bank, and the tidal wave move in counterclockwise direction around amphidromic point. Interesting investigations performed by several others shows that tidal current in the vicinity of critical latitude has boundary layer extended from sea bottom to the water surface. So then in this situation, if you would calculate the mean water velocity averaged over the depths, it will be much smaller than surface velocity of sea current. So then here you see more detailed map how tide propagate over the in this region. And as I mentioned, around amphidromic point, there is counterclockwise motion of the tidal wave, but around Bear Island, there is clockwise motion of tidal wave. And all circulation on Spitsbergen Bank is realized in a clockwise direction according to the simulation. So then you may see also simulated, recently simulated tides with many nonlinear effects provided with the model of Kovalik and Proshutinsky. So then you can see quite high velocities of water speed on the Spitsbergen Bank, about one meter per second. So, and here you can see trajectory of buoy deployed on the ice and afterward drifting without ice during almost 1 year. It's actually finished up somewhere in mid-Atlantic, but we managed to observe surface current in different regions of this Spitsbergen Bank. And you see when wind was small, buoy was just rotating on the same place. And it was a good possibility to investigate the speed of surface current with this drift buoy data, which were provided with time resolution 10 minutes. Each 10 minutes we had the position of the buoy. So, and what we discovered? So the first we discovered that the surface current is much higher than current predicted by TPXO model. TPXO model is standard tidal model, which is used by many others. And then the left figure shows that the blue points are associated with buoy data and the yellow points are associated with tide model. So difference is quite big. And the difference calculated with model of Kovalik and Proshutinsky is smaller. So, but still there is a difference. So, and the question is how we may interpret that, if it is related to boundary layer effect or there are some other physical phenomena which would explain that. So then we analyzed the vertical profile of velocity by IDCP deployed from the ship. And here you see this vertical profiles. So in some places profiles are quite visible, but in most shallow part, they disappear. So then when ship was drifting around the circle, and when it was at the depth around 30 meters, we measured good profiles, but when it was on the depth below 25 meters, profiles disappeared. So then I cannot tell that boundary layer effect can explain everything in this region. So then here you see difference between measured and simulated tide. Blue point related to mean depth 30 meters, yellow point are associated with the depth 50 meters. So then if we go on bigger depths, so then the difference between measured surface current and simulated current with tide model is smaller. So then ice condition in the region. So they are quite interesting because, as I said, ice stay longer in the region, and ice age is quite on the south. So then here on these three figures, you see ice map from 2017, 18, and 19 in the end of April, when we were in for the field works with ship Polar Cecil. And these blue figures show locations of our field works. So then what I wanted to tell more about ice conditions, I analyzed by ice maps, which were shown above on the previous slide, amount of days when ice was observed on 75° north. So in this white area on the left figure correspond the amount of these days, and you see that it is 150 days. So ice season is quite long. So then on the right figure you can see mean duration of ice season is 60 days, but maximal values could reach 150 days. And in this year also ice was on Spitsbergen bank quite a long time. So I will explain my vision why it has happened. So then here you see just trajectories of the ship, green line, blue line, and yellow line during our cruises when we provided measurements. So in some measurements were performed when ship was moving and we stopped for CTD, but some measurements were performed when ship was drifting just together with ice. So then you see image from 2017. The ship was moored near the ice in the shallow place of Spitsbergen bank, and we were working on this ice floor. So then you can observe ice conditions around. On ice map, it looks, ice looks very weak, but in reality, it is not so weak. So then here you see comparison of ice trajectories in 2018 and 2019. We were in slightly different places. And the next figure show a difference in the speed of ship. So then when we were in 2018 on shallow part of Spitsbergen bank, so then drift speed was about 1 meter per second and ship was rotating just along a circle. And gray area shows the drift speed near the Hoppen Island to the northeast, southeast from Hoppen Island in 2019. So then in 2018, when we were in the region shown here by blue line, we observe when we approach to this place, we observe a lot of big ice area, area of sea surface covered by slush. So I don't know how thick was this slush, but the amount of slush was very impressive. So, and after that, I made some observation by ice map and discovered that ice formed, discovered local formation ice on Spitsbergen Bank. So it means that ice is not drifting from somewhere on the bank, but ice formed just on the bank and then is growing, and that is a place for local formation of ice, which is located much more to the south than other regions in the Barents Sea. For example, when we don't have ice in Spitsbergen Fjord, we may have ice in Spitsbergen Bank. So then other floors you can see here, they are quite big. So you can see that thickness of some ice floors reach 6 meters and bigger, and I'm sure that that is consolidated ice ridges, which were formed some times ago, but when they arrived to the place, they became completely consolidated. So then in 2019, we were working on that floor to the south east from Hoppen, and it was completely consolidated floor with maximal draft up to 9 meters, so quite big. So then this is ship, blue line shows ship trajectory in 2018 when we were near shallowest place of Spitsbergen Bank. And black line show trajectory of buoy deployed in the same place. So that buoy was drifting there not longer time than ship. So then right figure show the profile of bathymetry with respect to the trajectory. So then we made CTD profiles and discovered that salinity and temperature profile in shallow parts are almost vertical, and density profiles are almost linear in the region. This, of course, with some small slope. So then we made analysis of Richardson number using KDCP data and discovered that in this part Richardson number was smaller than 0.25, and it means dynamic shear instability. So actually this dynamic shear instability was discussed in many papers that it could be in this region, but it was no data about that. And now we see that that is quite a good example of this effect, and this instability influence water mixing and stop heat fluxes from ocean to the air. And it influences fast ice formation and explain observed ice condition on the bank. So finally, I concluded that analysis of ice conditions showed that the ice can be observed for a significant period every year on Spitsbergen Bank. Criterion for comparison is the annual number of days when ice was found at 75 degrees of the north latitude. Most frequently, ice was observed there in March and April. Mean amount, so since 1998, annual number of days when sea ice was present and this latitude reached maximum 150 days in 2003 and was equal to 138 days in 2020, and in this year that is about the same. I didn't calculate that, but I know that ice was there up to recently. Minimum amount of number of days was in 2012, only 5 days in 2092, and the mean value of days is 60. the mean measured velocity exceeded the mean simulated tidal current velocity by 20%, and the maximum measured velocities exceeded the maximum simulated tidal current velocities by 50% when simulations were performed with TPXO model. So it means that other models should be used for this region to reproduce surface current. And that could be quite important, for example, for the iceberg drift and for the navigation. So then I mentioned that we discovered, calculated very small values of Richardson number, meaning mixing of water in the region. And this mixing drop ocean heat flux. We have cold water coming from the north in the region, and this water is well mixed. So then no heat flux to the air, and as soon as we have cold weather, we have a very fast ice formation in the region, and as a result, we have a very southern position of ice edge near Bear Island. So thank you for your attention, and here you see iceberg in the same region, so sometimes they appear there.
Thank you, Alexey. We have time for one question, please. Any questions, colleagues?
Alexey, one question. What about those ice flows with consolidated ice and rather thick? Are they multi-year or first year ice flows?
That is first year ice. We measured salinity, we measured temperature. It has normal salinity of seawater of sea ice 5 ppt, 4 ppt, 6 ppt. It may include some fragments of fresh ice from glacier, but usually that is normal first year ice, which was these ridges were formed somewhere and then consolidated on the way of their drift to Spitsbergen Bank.
Yes, thank you, colleagues. We have no time more.
Yeah.
I'd like to shift to all of us to room number 1 for closing ceremony, because all participants are waiting.
Yeah.
Thank you.
Thank you.
Okay. Thank you.
Let's go.
Thank you, colleagues. Yeah.
To room number 1.
Will we go automatically, or we should quit and then go room number 1?
I don't know exactly, but I think that we need to close this section.
Okay, then we do it.
And begin the second.